Now, I've lost track. What's the number? It is lecture 23. And we are ready to quantize the massless vector field. So it's 6-3. Last time we considered the Dirac spinner. Now we go straight to the massless vector field. So we discussed the classical vector fields also with mass. But since we want to get to quantum electrodynamics, so this is electrodynamics, this is the massless vector field, the photon. And then we go straight to the massless case. So free though, at this point, free massless vector field. And so since this is supposed to be electrodynamics, the equation of motion in the Lagrangian should be Maxwell's theory. So Maxwell, the equations of motion are, you write them in terms of the field strength F, like this equals 0. Or spelling it out, it's the nu, and this is the nu, a nu. So it's basically the box on the 4 components. And then we weren't happy with this. So minus well, right, like this mu. That's our equation of motion. And we saw that it follows from this Lagrangian minus order F mu F. Right, this field strength F mu is defined as this antisymmetric derivative of the vector field. And that's what I plugged in there. Why is this Maxwell's equation in electrodynamics? So if you write this thing in terms of the more familiar electromagnetic field, then this is 4 by 4, U is 0 to 3, and it's antisymmetric. There's nothing on the diagonal, and then you have B field in the time component. So my first index is 0, then I have the first index is time. I have my electric field, it's antisymmetric, so minus here. I can never remember whether the minus sign is there or there. Or you can also change it around. But let's say it's this. My B field in there. And also since they're a little complicated, so this is the component 1, 2. So then this should be 3. And then this is 1, 3, so that should be 2, and this should be 1. And then it also has various signs. Well, of course, here it's the opposite from there. And now taking a minus, 3 minus signs. And I guess it's all wrong because the conventions I chose in my notes is minus, minus, minus. So this you can write as F I0 is the electric field. So second one is time transaction, and these are the B components, and the Fij is Hij B K. Here's the sum over K. And if this is 1, 2, then it should be 3. So 1, 2 is going to be 3. If it is 1, 3, then it should be minus 2 because epsilon and so on. So if you define it like this, then these equations here, this first line, becomes, shall we do one or is this homework? I have to give it this idea. Well, if it's not homework, then it's optional. Or well, so I can choose the index u freely. So let's pick the 0 component. Then this is one equation, and spelling it like here. This is d 0 f0 0 plus di fi 0. But f0 0 doesn't really exist, so it's just this. And only mean this. Basically, it's down with minus sign, and this was the I, so this is the divergence of my field, and that's 0. Okay, so this is basically Gauss. So you see, it's a Maxwell equation, which you're used to in this form, that we have a 0, so we have vacuum. These are the vacuum Maxwell's equations. So this is one more equals 0. There's no sources in our theory. Later there will be sources. They're not there. And the other one, if this is an I, you get the curl of B is equal to mu J plus E dot, but with no current. So the other equation where this index is an I will be this equation. Yes?
I think it's not focused anymore.
It's not focused anymore. Thank you for. And how do I focus it? I'm hitting the autofocus button. But clearly doesn't. Was it focused?
No.
Ah. Thank you. So, right. And that's why we're calling this equation and this Lagrangian Maxwell theory. Because if you do this identification, you get the familiar equations. And now we want to quantize this. So come up with a quantum theory that's consistent and is based on these degrees of freedom. The first thing you would do is the canonical momentum. They are pi for all of them. So pi blue is equal to dl by d, and now we're going to put the index. So let's say downstairs is my standard one, and this canonical one, the pi should have it's upstairs because I'm differentiating with respect to downstairs. So downstairs is like upstairs, and this is not the A field, but it's velocity, the time derivative. So I need all the time derivatives in L. So let's see. It's hard to see anything if this is just F. So we spell L out. This is minus 1/2 d mu a mu minus d mu a mu d mu a not wrong, but I think I can do faster writing like this. So it's an F, the F mu is an F0, both are 0 plus F0I plus Fi0 plus Fij. Right, so I just put this into time and space. That's nothing because these components are 0 and these are the same. I switch them around. Maybe keep them, switch them around, you get two minus signs. And then they look the same, and then maybe also pull these indices down. Which gives me another minus sign. So this is equal to 1/2 Fi0 times 2. What's that? Minus 1/2 Fij. So two minus signs, and this minus 1/2 stays. One minus sign for pulling them down. Here and there. Two minus signs by switching them, adding the two goes away. And now, this doesn't have any times in it, no zero indices. This one though, and this is now I start with the A's minus D0 AI. And why was this a half? It was a quarter, so I have a half here and I have a quarter there, half there, and then the IA0 minus D0 AI plus no time. Do we need this? There's no time things here. No time derivatives. I might need this later for the condition of the Hamiltonian, but not for this derivative. So I'll get this. This is not the time derivative. This is one. These two together. It's 1/2 AI dot squared. And then we have mixed this with this. This is minus 1/2 times 2. Sorry, 1/2 times 2. AI dot times DI 0. And then plus other stuff. It's the same as here, plus one more term. So there's all my time derivatives. And you notice, disappointingly, pi0, A0 dot doesn't even occur. So pi0 is just 0. Like DL, DA0, again, upstairs, it's just 0. There's no A0 dot. There's just the spatial components. The spatial components appear as with their velocities in the Lagrangian, but not the product component. So the A0 doesn't have a conjugate momentum. And it's really bad. Because I would have liked to write down the canonical commutation relations, and they're usually in the field with its conjugate momentum. Supposed to be I delta 3 x minus y. This is what we would have liked for operators in my quantum theory, right? This is what I wanted. But if pi0 is 0, then is he seriously skiing? Yes. No. All right. Well, now I can't focus anymore. So if this is the case, then this operator should be 0, I guess. But then this is not 0. It's almost everywhere 0, but it's not really 0. There's still a delta function. So that's a contradiction. So this is all bad. 0 can't be non-zero. Well, the reason why the A zero doesn't have a conjugate momentum, why there's no time limit here, is because the A zero isn't really an independent dynamical field. This can be seen by looking at the equation of motion again. This one, the one with the zero, like this one equals zero. But in terms of A. So let's write this one more time. But not going to the E and B's, just stick with the A. So in the equation, do I erase? What's most logical, given that you're evaluating my pedagogical skills in 90 minutes or in 75 minutes, so I better do this right. So consider even a word. See, consider equation of motion for mu equals 0, as we just did, but not going to E and B. Then I have d mu a 0 minus what was it? D0 d mu a mu, like this. Now again, split into temporal and spatial parts. This is d0. Yeah, this is 0, 0. And since 0 can be up and down, why not putting it down? D0 squared of A0 minus this thing, A0. What's that? This is like box. Also right. Dot. So that's this term, and then minus D0, 0. That's again an A. So this is 0, 0 now. So then it's two time derivatives on the 0. And then I have a plus D0 of II divergence. That's all equal to 0. And the umlaut goes away. And then I have the divergence, or sorry, that's Laplace of A0 is equal to the other side, the divergence of the spatial components time derivative. So that's the equation. This equation, an equation of this form, is called Laplace equation, right? Laplace. In fact, if there's an homogeneity, you call it the Poisson equation. We're doing this in academics all the time. So if this is given, you find this. And you know the answer. The phi is some integral over this thing with the Green's function and so on. So, but what I'm trying to say is, if this is given, then that's fixed. So my A 0 of x, so A at some time t0 yields a vector of x and its derivatives, its time derivative, maybe there, time derivative, a vector dot is given, then at this time, I know what A of x, A0 of x is. Namely, it's just the right-hand side, this is inversionality, divergence of A x prime over the Green's function. If you don't know, you don't remember your electrodynamics anymore, then that's fine. This is not the most important thing, how this looks like. In fact, we'll be talking about Green's function in a minute, no, in a week or so. Yes.
Should it be a dot in the?
Should be a dot because it is copied from here. This is the inversionality. I put this in there. It's basically my sources and then like electrostatics. This is the equation for the electrostatic field. This is the charge density, and then you have this thing. So we'll be talking about Green's functions, and this is really only to say that once you know the vector part of your vector field, like the spatial components, then you also know the temporal component. It's not independent. This means we can't specify an initial function x a0 and a0 dot independent of the others. It's just a consequence of the equation of motion when the others are given. So this is not really independent dynamical. And therefore, it's a bit awkward. The point zero is zero. So we understand why this is so. We still don't like it. Because we only know our canonical quantization program. But now we know that it's gone, my Lagrangian. The theory has this gauge invariance. So you have the gauge symmetry. If the A mu changes into a new field, which is the old field plus the derivative of some function, then the equations of motion the field, the equation of motion, yeah, they don't change either. My field don't change. So the F, well, we've done all. Do you remember that? The F under this goes into an F prime, which is defined in the same way as it was. So it's d mu a mu prime minus d mu a mu prime. But if I plug this in here, this a, of course, I would use the term with the a replaced with the a prime replaced by a's, and also extra terms here, but they cancel because you have d mu on alpha and d mu on alpha and the minus alpha. So this is the same as there. So the field strength is the same for the A before your gauge transformation and after. And since the equation of motion was this, d mu f mu mu, they also don't change. So we could play with this. What is it? It means, as we did say, you have a redundancy. You can choose to describe your physical situation in terms of this A or this A. They look very different because you add this function, but they describe the same thing. So you may impose something else, the gauge condition. You say, I want to work with this or the other thing. And in fact, where's my equation? This is already, so in fact, I want to get rid of the second term. So I want to impose a gauge condition. In fact, Lorentz gauge. There are many, but I want Lorentz gauge. And this says the divergence of A should be 0. And earlier we showed that this is possible. If you have a field A whose Ford divergence isn't 0, then you can find a little alpha such that the new A prime has a 0 Ford divergence. So I can always ask for this. Okay. So now we have the equation of motion there and this condition. And now I think I want to change the theory by adding something proportional to this constraint, which is 0 somehow. Once you impose it, it's 0. So I'm first modifying the theory, which is then not Maxwell's theory anymore. It's all different, but when you impose the constraint, then it should be the same. I guess the picture is this. You have L Maxwell, and we want quantum theory, like quantum theory for photons or for the gauge field, right? But here, my direct approach by computing the pi's already failed. Like I couldn't just do it. So now it's a detour. We'll go to some other theory of prime, which is not Maxwell, different. It is the same if you, in addition, impose the constraint. But now I'll forget. So this error, this detour means I'll forget the constraint when going down to the quantum theory. So I quantize this thing. And then I have quantum theory for, well, here, let's say this is Max. And this is the non-Maxwell theory. And then we go back, imposing the constraint. This Lorentz, let's call this the constraint. Well, we'll do it at the operator level, so we'll have a hat on it. And here I'll call this constraint. Which is this. Just to, talking about. Here we are quantum, so we have operators, and then we impose this. And then we have a quantum theory. And since this is really not there, we have no way of checking that this is the right thing. It's just something. It's a consistent theory that we will claim it is the one. And if we get photons of the right polarizations, massless, then that's all we wanted, and then we're confident this all makes sense. Okay, so that's the roadmap, and what's my modified theory? So this is what I had as mu nu, and then I add, well, people add this, d nu a mu squared. So you see, I deliberately write this term into the Lagrangian, which is 0. If I impose this gauge already here in the I wouldn't have added anything. But that's not what you're supposed to do, right? You're not using the equation of motion or constraints in this Lagrangian. This is just the Lagrangian defines the theory, and then you derive the equation of motion from there. And then, if you want, you can work with something imposed to constraint. And since this is a square right there, the equation of motion will have this term in there. So if I, in the equation of motion, use the constraint, I should really get the same we had. And this is a zeta, more or less. It's just a parameter which we can choose, because this is essentially a zero. And it'll turn out that zeta equals 1 is a great choice, but let's see first why this is solved by having it arbitrary. The equation of motion.
Excuse me, can you tell again, like, what's the problem with this equation of motion we just derived?
With this equation of motion, there isn't any problem. This was my way of giving a reason why there is no momentum, no canonical momentum, essentially no velocity for this zero field for this guy. This is a nice field like the others, but it doesn't have a conjugate momentum. It's not the same as the others. It behaves differently, and it doesn't have a. Oh, it's gone. In the Lagrangian, there wasn't any time derivative. So usually you're supposed to have a kinetic term, and they're usually what are they? A half v squared, right? So this is at least what you have. You have a velocity there, and then maybe a potential. And there are different scenarios. If you don't have a coordinate dependence, then you're happy, because you call it a cyclic coordinate, and then you have the conservation law, and everything is nice. Like just the velocity is okay without the coordinates. But if you have only the coordinate without the velocity, then you go like, ooh, then this is missing something. It's missing the dynamics. What is it? It's sometimes called a Lagrangian multiplier. If you have whatever different one, L, which is an x times whatnot, times what? Times letter A, B, C, D, C is good. This stands for whatever, but not other x's and x dots. Then you derive the equation of motion, and the equation of motion is just the part with the dl by dx dot is gone. It's just L by x, so it means C is 0. So this extra thing is the Lagrange multiplier for the constraint that this is 0. Right? If this was a field, right? If we claimed this was a dynamical thing, this zeta would be a Lagrange multiplier for the constraint this equals 0. Right? The variation with respect to zeta is this, and then set the variation to 0. So anyway, what I'm saying is, if there's no velocity, no time derivative of your dynamical field, then it's not a dynamical field. It's a Lagrange multiplier for something else, for a constraint. And that's what happened to this poor A0. And so it doesn't have this first term. This is the first term in the equation of motion, right? This is this dl by dx dA dot. Right. So here it is. If the vector part is specified, then this has no choice rather than being. You can also forget about the whole story and just see, oh, this is 0, and I can't impose my canonical commutation relations. And now, what do we do first? I want to do 2 things. don't know the order. I want to write the equation of motion just to see what I'm getting, and then compute the canonical momentum and hope that it's not zero. Why do I think it's not zero anymore? Because here I put in a time derivative of a zero, right? This thing is a zero dot minus I don't care, minus something, but there's suddenly x zero dot with a square and a half. Oh, beautiful, right? So this is exactly my kinetic term. That's why it's there. Now with this modification, you have a non-zero pi zero. But before deriving the pi, oh, this is L prime, right? This is not Maxwell theory. This is only the modification there. But before doing this, I want to see what the equation of motion are in order then to argue that beta equals 1 is a good choice. So delta L prime is, I know someone asked me, is this like an operator? And now I'm doing what I didn't want to do. I just have to get past my equation of motion. So this is delta F mu twice. And then I have here minus beta mu a mu e mu delta a mu, and I don't like the mu here. This and this is the minus 1/2 x mu d mu delta a mu minus d mu delta a mu minus what I have here, d mu a mu. These two terms can be made equal because f mu is antisymmetric. Which one do you like better? Stay the second, because this has an a mu and this has an a mu, so let's get rid of this one. So in this first term, I relabel mu and nu. I label mu and mu, which then gives me here this thing and here this thing. So now the second line is the same as the first line, just with the dummy labeled, this is relabeled. And then I turn them around at the expense of a minus sign, which is same as this minus sign. So now the first and second is the same. So I can drop the 2 and just write the second. So it's f mu delta a mu minus beta mu a mu d mu delta a mu. Now I guess isolate the delta a mu by integration by parts. So this is equal to minus the mu f mu in the first term plus zeta e mu d mu a mu, and the whole thing times delta a mu plus the surface terms for my partial integration. So I have surface terms. We call them 4 divergence. And they don't matter in the equation of motions because I vary the action, and the integral over this 4 divergence is just a boundary term, and the boundary I don't vary. So I get this thing equals 0 as my equation of motion. If I turn this around, it looks like we have before E mu mu plus zeta d mu d mu a mu. And why is my index so weird? I'm so sorry. I can't pull this out because here it would be an upstairs index. Then it has to be up. Let's do the upstairs index because it's upstairs. And this one needs to be upstairs, so that needs to go down. Now it looks better. Turn them around. Mu equals 0. That's my equation of motion. It looks, it has gotten this extra term. If theta is 0, I haven't done anything, so this is gone. And I get the old one back. But also, if I impose the Lorentz condition, then that's 0, and it's also gone. And this survived, this part, because it was squared above. If I had only one, it wouldn't. But now, since I have two of them, one remains, because I have one variation, so one remains. And so this is, it doesn't bother us. So that's cool. We have this extra term, but upon using this constraint, I get the old one. So this theory isn't Maxwell. It's not like I wrote Maxwell in a different gauge or so. That doesn't exist. The theory given by that first term is Maxwell's theory, and that is gauge invariant. You can write your A in different gauges, but that's this theory. Now, with this term, it is a different theory, but the different theory with the constraint that is the for the Maxwell theory, the Lorentz gauge, they become the same. And how does this look now? A little bit more explicit, because I want to fix this number. You can also keep it arbitrary, and some people do, but then it's lengthy computations. There's a nice choice. So let's write this out again as we did earlier 2 times. This is d mu a mu minus d mu d mu a mu plus this one. And now you see that's essentially the same thing because I can switch them around. They're the same. Let's make it even more obvious. So I have box a mu plus zeta minus 1 d mu a mu, right? Now you see why I want to choose zeta equals 1. If I have zeta equals 1, my modifications from there, but the equation of motion become even simpler, right? We had this equals 0. We added stuff to it, which makes it more complicated. But with the right choice of zeta, it actually, this complication takes away some from here and makes it simpler altogether. So let's choose now, choose zeta equals 1. That's called sometimes Feynman gauge, which is confusing because this is not a gauge invariant theory, right? This thing isn't gauge invariant with the gauges we had before, because the mu a mu isn't gauge invariant. In fact, this breaks the gauge. It determines which A you want to use on a gauge orbit. So this theory is not gauge invariant, and calling zeta equals 1 Feynman gauge is kind of confusing, at least. But it means, well, a certain modification, which is nice and simple, and it leads you to Maxwell theory in Lorentz gauge. Actually, the other features as well. Now, if we pick this, then we have Now, what do we have? Our non-Maxwell theory. Let's write it. The modified is taken to be, right? Our choice. Nobody forces us. It's just guessing. And people have done this before us, so we know what it looks like. In fact, Fermi did. What's this idea to add this term? So it is minus f mu nu f mu nu minus 1/2 d mu a mu squared. Yeah. With this equation of motion and this constraint. So this follows from there, and this is our extra condition that brings us back to Maxwell. That's extra. Now, if I computed the pi from this thing, I would find a non-zero pi zero would be non-zero, and the pi I would not have changed because this term here, this extra term doesn't add any time derivatives of a vector. So it just changes the zero component. But it is not nice. I did it, it is not beautiful. So we can save ourselves some pain by actually making a second modification as well while we are at it. So let's not compute the pi's just yet, but let's look at how this action looks like in terms of just these a's. So then we have, how many times have I done this now? So this is minus 1/4. Wait, I'll write d mu a mu d mu a mu d mu a mu d mu a mu minus 1/2. And here I also want to do it. No, let's do that. D mu d a mu squared. And now here, the first two together, I want to multiply it out. The first two together and the last two together give me the same thing, just with other dummy indices. Here derivatives are contracted and the field, and here also derivative and field. It's just different not letters. And minus minus gives plus, so it's the same thing. So I can write minus 1/2 d mu a mu d mu a mu, and this is now both the first two together and the last two together. Now the mixed term, this with this, let's write it. It's d mu a mu d mu a mu. So now derivative with the other field and derivative with the other field. But that's also here the case, just in the other order. And they both have a minus sign, and this kills this minus sign, and they have a factor of 2. Well, it looks like this. And here, funny, if I take this apart, rather than a square, I get this. I have to relabel it because 4 views isn't good. And now I have all the combinations. Which one do you like best? It looks fair to have everything, but there's a clear favorite. What's your favorite? Do you rather want the derivatives connected, or like this cost thing, or this? Okay, with what goal? Let's write down the Lagrangian. Here we're writing a Lagrangian. What's the Lagrangian for a scalar field? So what was this again?
Box.
No.
Okay.
If you do a partial integration, you could probably get away with the box, but the box, we never wrote it as a box. I'll come back to this just to make it a true statement. I know you know everything about the quantum Dirac spinner, because that was after, but the scalar field was before Christmas. How about this? 1/2 d mu phi d mu phi. And then if you wanted, minus half m squared phi squared, but okay, here, in box is this. I could, partially integrate it and then do phi, box, phi, right? Sort of, you have two derivatives and bring this to the other side and then plus, whatever. So it wasn't wrong. But this is the way we used to write it. And now which one do you like best over there?
The last one kind of looks like this, but I don't.
The last one doesn't look like this.
Okay.
Because here the derivative and this derivative, they are contracted.
And the first one
And
looks
here-
like this.
Well, you want to
Yeah, I
say
want to
first,
say-
right? So we can add many scalar fields. Let's add index I. So now the derivatives go together and the field goes together. That's exactly what we have here. So this, okay. The minus sign, oh God, whatever. The minus sign is okay, because if this is the spatial part, then you lower it, you get an extra minus sign, so forget the minus sign. This is our favorite. And let's bring this, we can't even. Okay, so this is good, and let's get rid of these. How can we get rid of these? They connect the derivative with the field here and here and here. Here's basically the next to each other, and here they're kind of awkward. The derivative acts on another field than its index is connected to. Partial integration, right? So let's look at this term here. This. This is equal, so I'm copying it, d mu, a mu, d mu, a mu. Now, let's take this to the front. Then we have 1/2 d mu d mu, a mu. So if I multiply this out, this goes to the second and with this term, but I don't have the other one, so I subtract it. So it's minus 1/2 d mu d. Where's the index of mu a mu a mu? Right. So this is the partial integrated one. The mu that was here on the second has moved to the first. I've gotten a minus sign, and that's the surface term that I didn't write before. I wrote it now for no reason, because I could. And now we're halfway there. This needs to go to the other side. I'll do the same trick again. 1/2 d mu d mu d mu a mu minus 1/2 d mu d mu a mu a mu plus 1/2 d mu a mu d mu a mu. So this is the interesting one. Here the mu has come to the other side, the sign has changed again, and I produce another surface term. So the one with the star, that second one, is equal to this plus the 4 divergence. Yes?
I think the one partial derivative, d nu in the first term should be an
Yeah, that looks funny. How did I do this? I copied it. Thank you. I could, I don't know, if I have the time, make this even more obvious. So we didn't have a speaker. No, not today, we do actually, because I have. So maybe also. New, and then, split them, and here, this is really just one. This can be written as one global four divergence, so I can choose mu, and then I have half. And if this is a mu now, then I better relabel everything, mu, a, mu, a, mu, and here, this goes up, so it this needs to go down, d mu, a mu, a mu, boom. So this is equal to this plus one four divergence of this thing. But this, you see, is that second term with the other sign. So basically, this minus this minus this is the four divergence. The whole second thing, the ones that you didn't like, is really a four divergence and doesn't contribute to the equations of motion. So why not just dropping them all together? Because they don't contribute. Is this allowed to just drop them? Yes, no. I don't, it depends. What does it do? These extra terms, they do contribute to the conjugate momenta. Right? So in that sense, no, you shouldn't. Because you're changing something. But you don't change the equation of motion, as we said. So from that point, if you only care about this, then change it. So a different theory, now L double prime would be just the first term. With nothing else. I could write it here. So here, if what follows is box A equals 0. Quite trivially, because this is it's now four scalar fields. Just let's be honest. We have now massaged this for an hour, so that we have four scalar fields, which is the only thing that we really know how to handle. And the rest was just justification and storytelling, right? So this is what I wanted to start. But since the gauge field or the vector field, the Maxwell field isn't just the collection of scalar fields, you have to have something extra, because this is not Maxwell theory, it's just four scalar fields. But the four scalar fields become Maxwell up on this extra thing here. So now, from there to there, also to be honest, I do change the pi's, the conjugate momentum densities, but I don't want to. Because as I said, they were more complicated here, and they're simpler here. So I choose this thing. And depending on which book you look at, you find one or the other. Like Pescatore, you don't find anything, because he says it's. Well, there's a chapter where he just writes down the Feynman rules so you can already work with the quantized theory without deriving it. And then when he later derives it, he uses not the canonical quantization. So there's nothing. In the other one that we use, this Edelhäuser, there they use the complicated version. This, however, then they don't do the interesting computations like the Hamiltonian, and because the Legendre transformation needs the pi's, right? roughly speaking, actually precisely speaking. And if they are ugly, then you have to work more, and he just skips that. And then there are other references like Greiner, he just goes the second step, and I'm following this approach because it's simpler and we can actually do it. So here we go. What is the pi? Pi. Let's write it first more explicitly. The time part. Let's write the time part. It's minus 1/2 a mu dot a mu dot plus 1/2 gradient a mu times gradient a mu, right? I have split the mu index into time and space and get this. And now it's easy to see what the pi mu is, which is dl by dA mu dot, because it's just this thing here, right? It's minus, so up and down. If this is down, I'm differentiating with respect to this field, but the lower index, so the upper remains, and then I have a minus sign, and then I have the other one, switching, a mu dot. Oh, how wonderful! The pi is the velocity. The momentum is like it always had to be. Here, where's my scalar field? This is the same, right? The pi was always pi dot. This is how you p is equal to x dot. This is the given. The minus sign is just awfulness of the metric, and it doesn't bother me. Let's write it the other way. Let's split the mu index rather than the mu index rather than the mu index. Then I have minus 1/2 mu a0 mu a0. So that's like this here, my scalar field with the wrong sign. And the spatial, what happened here? I don't know what happened here. This is who generously allowed me. So anyway, here I put it down because I can. It's time, and then it's the other plus 1/2 d mu a I d mu a I. So if I pull down an I have a minus sign which changes to plus. So this is the normal canonically normalized plus 1/2 kinetic term for a scalar field, for actually 3 scalar field, summed over I, and this 0, has the opposite sign. So that's why the whole thing looks like with the minus sign. And then it so happens. All right, now we're ready. Oh, the Hamiltonian, we still have to find the classical Hamiltonian, and then we're ready to propose the quantum theory. Now the H is what I just wrote, I mu a dot mu minus L, and this is minus so let's keep the pi here, and the dot is minus pi. And then I have minus L, and L is this, or this really, it's either way, it's minus, so it's plus 1/2. Quick or no, not quick. A mu minus 1/2 a mu, but these are again the pi's, minus sign here, minus sign there, doesn't matter, so this is pi squared. Here it's pi squared with a minus sign, there's a half, so it's minus 1/2 equal to minus 1/2 pi squared. I write it pi mu, minus, yeah, minus, minus 1/2 a mu times a mu. One more time if you want it, minus 1/2 I 0 squared minus 1/2 a 0 squared plus 1/2 pi I squared. If you have an I, putting this down, just a plus sign, plus 1/2 a I squared. So now we have four scalar fields, and one with the opposite sign, and that's going to haunt us. That minus sign, some minus signs of this type. Now, quantum theory. Let a mu and pi mu satisfy this stuff. A mu x pi. No, that was the most interesting one. This is the most boring one. Pi mu pi mu and a mu pi mu
Delta Menü Delta X minus Y.
delta mu delta x minus y.
And maybe some scaling factor.
Which one? Let's say this is an exam and you don't remember your scaling. And you remember your p, you remember your p vector, like in all quantum mechanics,
AH squared.
minus I h bar dx, right?
Yes.
And so this is the coordinate and coordinate momentum. And so what's left? You have minus I h bar x dx in the first order, and then we have plus I h bar dx x in the other order. You should think of this as another function, right? So this thing is equal to 1 plus x dx, right?
Yeah.
And then this and this cancels, and so I have I h bar 1. So coordinate with momentum is I times 1. What do you like?
I and then,
Yeah.
I mean, H bar is 1.
Exactly. So this is how you figure out whether it's I or minus I. And the Hamiltonian is d3x of this. Let's do the short version or the long version. I guess the short version. 1/2 I mu plus 1/2 a mu a we could also insert this thing now, like the pi is just a dot like it was, then okay, then it's just, then we get a minus sign here because this is extra a dot. And here it's just a dot and a dot. So the time derivatives commute and the one with and without is the delta function. Yes?
There should be a minus between.
You're kidding.
Right?
Which terms?
In the lowest, yeah.
Why did I get this wrong? There's the minus sign. Is that the right minus sign? Well, I wrote it, right? Alright, thank you. I need to give you 15 minutes, so I need to find a point, a good point to stop. Might be a good point to stop. So just to keep it exciting, let's just sketch what we'll do tomorrow and where the interesting bits are. This is a delta function. This means just 1, 1, 1, 1, right? They have to be the same. But if I do look at this here and I write it for a mu x and a mu dot, right? The pi is a dot, and I want to lower the index. So if I lower this index, then I have to multiply this with a metric, and then this thing will become a metric. There's the minus sign from here, so it's minus I, and then eta mu delta 3x minus 1. And so my scalar fields, these 4 scalar fields, satisfy what normal scalar fields, oh, it's not there, would satisfy, but one of them with the opposite sign, namely the 0 component, right? There's one sign for all of them from here. And there's another sign from here for the spatial ones. So the spatial ones are the good ones. The temporal one, of course, time special is the bad one. The time derivative is bad. So we'll find, when we go to the oscillators, we'll find relation operators. 3 of them are good for the spatial components. And then the time component is an oscillator that somehow has a minus sign. And we have to figure out what this minus sign means. It's a different type of minus sign as in the spinor case. There we had to go and solve it with anti-commutators because it made the eigenvalues of the Hamiltonian all positive. Here, the Hamiltonian, this one, will have only positive eigenvalues despite these different signs. So that's not a problem this time here. But my oscillators will here have a different, for the time will have a different sign in the commutation relation, which makes them their norm negative. So that's basically what we need to resolve. What do we have to change to make the norm of all states positive? And it's very interesting. Here we have 4 degrees of freedom. Like we have 0, 1, 2, and 3. And by imposing this constraint, which we haven't done yet, like this thing, will somehow kill something from here, and in particular the negative norm objects. This was just sketchy. We'll make this. It was a preview, right? I'll do this in more detail tomorrow. So now I'll stop the recording because of this course evaluation. Yes.